So chapter 14C. This is the last part of chapter 14. So this covers these topics of what are called maximal and prime ideals. These are specific types of ideals which are connected to specific types of quotient rings, which will be relevant as we go forward. Something we do a lot towards the end of the course is construct quotient rings that have certain properties. And knowing things about the ideals that we use to construct them turn out to be very relevant. So I'm just going to do a definition of each, prime and maximal, in reverse order, and give examples and non-examples, and then give the relevant theorems that we'll be using later on. So first definition. So a proper ideal, A, in a commutative ring R, is a maximal ideal. Let's say a maximal ideal of R, to be specific. If whenever, this is a weird definition, but I'll give it and then I'll clarify it. If whenever B is another ideal with A contained in B contained in R, we have B equals A or B equals R. So a couple notes. This only applies for proper ideals, so using R itself doesn't actually make any sense. You don't actually need the term proper ideal. It doesn't actually really matter, although it makes a statement vacuously true if A were the entire thing. So this is why it's excluded. The second thing is, I won't list that as a note. I'll just sort of keep it as a, well, actually let me put it because it's sort of interesting. So A must be proper or else the definition is vacuously satisfied. This we don't want for various reasons. The second note is this definition is only used for commutative rings, at least for us. If you have a non-commutative ring, things get a lot more complicated. So R must be commutative or else this doesn't make sense. I won't necessarily list that. But what I do want to mention is another way of looking at this. So this definition that it's maximal if whenever B is whenever B is such that A is contained in B is contained in R, B is either A or B is R. The way to think about this is that there's nothing between A and R, basically. The idea is that there's no ideals between, I'm going to put this in quotes because the word between is vague, between A and R. In other words, i.e. we don't have this sort of picture. Right. And so the other thing is typically the way this is proven, typically let's say to prove that A is maximal, and we'll do this. What we do is we assume that we have a B which is bigger than A, strictly bigger than A, and then we show that B must be R. So typically to prove A is maximal, we take a B with A contained in but not equal to B, and we show B is R. Now, there's another note I want to put with that, is to show that an ideal is the entire ring. So typically, to show that B is R, we show that 1 is in B, because then everything is in B, because then for all R in R, R is 1 times R, which therefore must be in B. Remember, the definition of an ideal is it's a thing that if you take an element in it and you multiply by anything in the ring, you get something in the ring. So this way this works. Now, this only works if the ring has unity, which isn't necessary for a proper ideal, but that's such as the case. So let's say, here are some examples. Examples and non-examples. So for example, 6z is not maximal. It's actually better to do a non-maximal example than a maximal example first. Is not maximal in z because, for example, 6z is contained in and not equal to 2z, which is contained in and not equal to z. So the way to see this is that 6z is all the multiples of 6. All the multiples of 2 contain more stuff. They contain, for example, 4. So this is an ideal. 2z is strictly between 6z and z. So therefore 6z is not maximal. So a second example is that 7z. Now you'll notice the 7 is prime and the 6 is not, and this is what it's going to allow this here. This is not maximal. Oh, sorry, this is maximal. This first one is not. This is maximal in z. So to prove this, because I'll prove this, it takes a fact that's necessary from number theory. So I'll point this fact out when we get there. And I think we've used it in class at least once, so this shouldn't surprise you. But in any case, to show that this is, let's assume that there exists a b such that 7z is contained in and not equal to b, which is contained in z. And we're going to claim that b is z. And what we'll do is we'll show that 1 is in b. So then we say, what does it mean for 7z to be contained in and not equal to b? It means there's something in b which is not in 7z, right? So this guy contained in 7z contained in but not equal to b implies there exists something, let's say little b in b with little b not in 7z. Then we say, okay, what does it mean to not be in 7z? It means you're not a multiple of 7. So b is not a multiple of 7. So that means it's relatively prime to 7. Now, the GCD of two things can be written as a linear combination. So in other words, this is a number theory fact. Thus there exists alpha and beta in the integers such that 1 is alpha b plus beta times 7, like a linear combination of the two. Now, for the last step, it's a couple things to note. Right? So these are easy, but you have to be careful about noticing them. Right? So the first thing to note is that since little b is in b, alpha b is in b. This is because alpha is in the ring. Actually, let me say that specifically. So let's say be really specific. Since b is in b and alpha is in the ring, alpha b is in b. And the second thing is since 7, so 7 is in 7z, and I'm crossing all my 7s, and that's going to annoy me. I'm going to go back and cross all these. That'll make me happy. So since 7 is in 7z, which is contained in but not equal to b, 7 is in b. And since beta is in z, beta times 7 is in b. So therefore 1, which is the sum of those, is also in b. And so then just to clarify this point back over here, since 1 is in b, if you take any integer, since 1 is in B, x times 1 is in B. Right, x is the same as x times 1, and that's in B. So B is R, or the whole ring, Z, QED. So that shows that in this case, the 7Z is a maximal ideal in Z. So one last example. I want to do this specifically to make a point at the end. Is so the ideal generated by X. This is not maximal in Rx, and this is because the ideal generated by X, this is a subset but is not equal to the ideal generated by X and 2, which is a subset but not equal to Rx. So I need to fix this. There's an error in this. I have to fix this on the lecture notes too. These should be Z's. So the reason is, let me just point this out about, just so we're clear on these, in case you've forgotten. This guy, the ideal generated by X, is the set of things that are X times polynomials in Z of X. So all of the things in here have 0 constant term. The things in here, in those we could take linear combinations of X and 2 using polynomials as coefficients. So what we get in here is, we saw this before, this is things that have even constant term. So it's fairly clear that we have this subset but not equal to, because for example, you can have a constant term of 4 and be in the thing in the middle. Right? But then of course this is all polynomials. There's all polynomials over here on the right with integer coefficients. So like in the third one, you can have, of course, an odd constant term, which you can't have either of the first two. So this is why this is not a maximal ideal. And all of these are ideals by definition, right? They're ideals generated by X and the ideal generated by X and 2. So that's the definition of a maximal ideal. So now let's look at the definition of a prime ideal. So again, we're going to have a proper ideal of a commutative ring is a prime ideal of R. So here's the condition, that if you have a product, this is a proper ideal A, let's be clear. If you have a product which is an A, one of the two things must be an A. So in other words, if whenever A, B is an A, we must have A in A or B in A. Now, notice here, just to be clear, A and B are things in the ring, of course. Everything's in the ring. So let me just dive in and look at a couple of examples. So I'm going to actually look at the same 3 examples just because it points out a difference and points out similarities and differences, right? So 6Z is not prime in Z. And this is because, for example, 2 times 3 is in 6Z. But 2 and 3 themselves are not in 6Z. Now, what you see here is that this is sort of like the definition of being prime. So you start to see this analogy, like, well, look, if it's it looks like if it's not a prime ideal, it's not a maximal ideal because of this behavior. And we see it the same with 7Z is prime in Z. And this is because, so we'll do a proof of this. Suppose that A, B is in 7Z. Oops, that should be a 7. So what that means is that A, B is a multiple of 7. So 7 divides AB. Now, it's another fact from number theory that if a prime number divides a product, it must divide one of them. Thus 7 divides A, or 7 divides B, and whichever one, or maybe both, will then be in the ideal. And I just realized I wrote a Z back here too. This should be a 7 as well. So thus either A is in 7Z or B is in 7Z. Now let's look at this last one, because the last one, right? So right now we've got two examples, and they're either the example is both prime and maximal, or it is both not prime and not maximal. So let's look at the X again. So here's the deal, is that the ideal generated by X is prime in ZX. It was not maximal, but it is prime. So to see this, let's just take a look, right? So to see this, suppose that a product, P of X, Q of X, is in the ideal generated by X. So this means that the product has 0 constant term. Let's say it has constant term. But what happens when you multiply two polynomials? The constant term of the product is the product of the constant terms. Right, so the constant term of P of X, Q of X is equal to the product of the constant terms. So one of them must have constant term 0. At least one of them. That one will be in that ideal. Or both, if they both do. So what we've seen is that you can be, like in the specific cases of Z, the prime and maximal look like they were the same. But in this other case, we have something which is prime but not maximal. So this might make you wonder if you could be, let's say, this question which is looming. Could an ideal be maximal but not prime? Right? We've seen prime but not maximal. But the question is, could it be maximal but not prime? So we'll have an answer to this in a second. We have two theorems now to look at. So I'm going to give each of these theorems its own number. So these are theorems that connect the type of ideal, prime or maximal, with a statement about the quotient ring that results. So the first one, and now both of these theorems require that R has a unity as well. So in this case, we'll say let R be a commutative ring with unity, and let A be an ideal. An ideal of R. So then R mod A is an integral domain if and only if A is a prime ideal. Of R. So the proof is actually, even though it's an if and only if, both directions are actually fairly sweet. So here's the forward direction. So let's assume R mod A is an integral domain. We claim A is prime. So to do this, we're going to assume that a product is in it. So suppose that AB is in A. We claim A is in A or B is in A. Well, so AB being in A, this tells us, this implies that the ideal, or the coset rather, AB plus A is the coset 0 plus A. But AB plus A is A plus A times B plus A. So this tells us that A plus A times B plus A is 0 plus A. Now this is a statement about the quotient ring, right? So R mod A is an integral domain, so one of these must be 0. So since this is an integral domain, either A plus A equals 0 plus A, or B plus A, or both, equals 0 plus A. And in the first case, we would have A is in A. In the second case, we would have B is in A. And that's the end. That's the end of the forward direction. And again, the thing to keep in mind here is that it's this statement that's coming from the fact that R mod A is an integral domain, is that when you take two things in R mod A and you multiply them and get 0, one of them must be 0. So backward direction next. So for the backward direction, we're going to suppose that A is a prime ideal. And we're going to suppose that A plus A times B plus A is 0 plus A. And we need to claim that one of them, A plus A equals 0 plus A, or B plus A equals 0 plus A. Or possibly both, of course. That's how we would show that R mod A is an integral domain. So then we say, well, A plus A times B plus A is AB plus A, and that's 0 plus A. So AB is in A. So either A is in A or B is in A. This is because A is a prime ideal. I'll just put this right here. Because big A is prime. Remember, prime means that if a product is in it, then one of the two things is in it. So in the first case then, when A is in A plus A is 0 plus A, or B plus A is 0 plus A, QED. So now we have this sort of tie-in between the quotient ring being an integral domain and the ideal itself being prime. And just a little note here is that we have to have a unity, because R has to have a unity so that R mod A has to have a unity, and R mod A has to have a unity because an integral domain is defined as being a commutative ring with unity, such that there are no zero divisors. So even though the unity doesn't get used in the proof, it's necessary to even make the statement that R mod A is an integral domain. So the second theorem, you might be able to make an educated guess about where this is going. The first theorem gives us a tie-in between integral domains and prime ideals. So you might guess that the other one might give us some tie-in with A being a maximal ideal, and it does. So we'll say let R be a commutative ring with unity, and let A be an ideal. So then it says then R mod A is a field if and only if A is a maximal ideal of R. So fields are sort of better than integral domains. Fields a ring in which every element is a unity, has a multiplicative inverse. So again, same deal. Let's do both directions. This is slightly longer than the other one, but not particularly difficult, right? So we'll suppose that R mod A is a field. We're going to claim A is maximal. So remember how we show that A is maximal. The classic approach is I assume that I have something bigger, and then we show that it's everything. So suppose that A is contained in and not equal to B, which is contained in R. We are claiming that B must be equal to R. That's how I'll show that A is maximal. Now, here's the deal. What does it mean for A to be contained in but not equal to B? Right? So just like before, with our example, since this is contained in but not equal to B, there exists a little b in B such that little b is not in A. So now look at little b plus the ideal A. Since B is not in A, we know that B plus A is not 0 plus A, and therefore B plus A has a multiplicative inverse in the field R mod A. So in other words, there exists, let's say, some C plus A with B plus A, C plus A equals 1 plus A. This is because R mod A is a field. And so just to clarify this, because R mod A is a field, this means that this guy right here is a unit, which remember means it has a multiplicative inverse, and that's the C plus A. So then we take that equation, we say therefore that BC plus A, I'm just rewriting this right here, BC plus A equals 1 plus A. So BC minus 1 is in A, fact about cosets. But then since A is a subset of B, we know that BC minus 1 is in B. But we know that little b is in B. There's a sort of a string of therefores about to happen, right? So B is in B. So BC is in B because B is an ideal. So then what we can look at is we can say, so then 1 must be in B because I sort of have this backwards. That's right, BC minus 1 is in B implies its additive inverse 1 minus BC is in B, and therefore 1 minus BC plus BC is in B. And therefore 1 is in BC. And so a 1 is in B. And since 1 is in B, B is everything. So that's half a QED. That's the forward direction. Right? So just to clarify, the end goal is to show that B is R, and we do it by showing that 1 is in B. And there's a little string of therefores at the bottom, which might be a bit confusing, but hopefully it made sense. So let's look at the other direction now. Let's look at the backward direction now. So now we're going to suppose that A is maximal. We're going to claim that mod A is a field. So this one's a bit more sneaky, right? So to show it's a field, I need to take an arbitrary inverse, an arbitrary element, and show that it has a multiplicative inverse, right? So let's let an arbitrary non-zero element. So let's let this the arbitrary non-zero element. We're claiming in the quotient ring, claim that x plus a has an inverse, meaning x plus a times something, some element, is 1 plus a, because it's a multiplicative inverse in the quotient ring. So what we're going to do is I'm going to introduce another ideal, and this bit, there's a small proof that's built into this that I'm going to omit. It's a good exercise. So what we're going to do is consider the following set. So this is the set of all Rx plus A's. So this is for this specific X, but R could be anything in the ring, and sorry, this should be a lowercase a, and lowercase a could be anything in the ideal A. So it turns out, this is a short proof, but you should try it. It's the ideal test, basically. It can be done with the ideal test. So a small proof shows that B is an ideal of R, but A is contained in and not equal to B. So the way to show this latter part, the latter part is easy to see. The latter part is simply because X is in B, but it's not in A. Right? So little note here, X is in B because X is 1 times X plus 0. So the short proof, just to clarify, the short proof is to show that it's an ideal of R. That's the bit that you should give it a go, because it's not hard. It's a fun exercise. The fact that A is contained in and not equal to B, that's easy to see, right? It's contained in it because, let's say, note, A is contained in B because for any little a is 0x plus little a, and that's in B. So the fact that A is contained in B is easy, and the fact that A is not equal to B is easy. It's the fact that B is an ideal that takes a little bit of work, that takes the short proof. Right? The point is that because A is contained in and not equal to B, we can say since A is maximal, and this is the case, we must have B equal to R. That's what it means to be maximal. If you have a bigger one, it's everything. So now, since B is R and R has unity, so since there's a 1 in R, we have a 1 in a B because B is R. So what this means is there exists an R prime and an A prime such that 1 is R prime X plus A prime. That's just from the definition of B. So now take a look at the product R prime plus A times X plus A. This is R prime X plus A. And R prime X is 1 minus A prime plus A. But A prime plus A, or negative A prime plus A, is the same as A. Right? So this can be rewritten, if you like, 1 plus negative A prime plus A. And this is A because negative A prime is in A. So this whole thing is 1 plus A. So now we have a multiplicative inverse right here of this guy right here. That's the QED. So now we know that if and only if we have R mod A as a field, if and only if A is a maximal ideal. So we can put these two things together to make a little final theorem. So here is a sort of a summary. Let me say this: summary and corollary. I want to add something else to the mix too. So far we've shown two things. Right? there are actually three things I want to list here. So we know that the first thing we proved is that, and this is again for R commutative with unity. The first thing we proved is that R mod A is an integral domain if and only if A is prime. Then the second thing we proved is that R mod A is a field if and only if A is maximal. But we also know that a field is an integral domain. In other words, if you are a field, then you are an integral domain. So this gives us the following corollary. So I'll give the corollary sort of with the proof built in. And that's the following. If A is maximal, this implies that R mod A is a field. This implies that R mod A is an integral domain. And this implies that A is prime. So what this means is that maximal ideals are prime, right? A maximal ideal must be prime. But the reverse is true, not true, as we've seen. And that's the end. So that's the end of chapter 14 completely.